Hello and welcome to another installment of Operating System from Scratch. This video is dedicated to tying up loose ends, so the table of contents for skipping to specific parts of it is of particular importance. The timeline is on screen now. In the description in this video, as with any other video in the series, is a clickable table of contents that will send you directly to the relevant chapter. I know of at least 2 people who, as a result of this channel, actually went out and bought an Orange Pi 02. I cannot describe how flattered I am that people care enough to follow along so actively. Just to be clear, none of that money reaches me. I am not affiliated with the Orange Pi project or the company behind it, and am not sponsored by them in any way, shape or form. One would assume that those people would like to actually get the code and run these steps themselves. While it is possible to pause the video and type the code in, I will not inflict this pain on anyone, least of all people enjoying something I'm working hard to create. As such, it's time to share the code in an easy-to-obtain electronic form. I think we all know what that means. QR codes. Why don't you just post them on GitHub? Did I ever tell you how annoying you are? Or I can post the files on GitHub. So the repository with all the files we created here is now officially available on GitHub. I'm releasing CellRes under the Boost license because why not? Share and enjoy. The repo has a tag marking the code state at the end of each video. This way, if you pull the tag, say bring up 4, you'll get the code as it was at the end of the previous video. The tag's comment, available with a git show command, also contains the URL of the video in question. I also have a prep repo where I run experiments until I'm sure the code is ready for public consumption. I'm thinking of offering access to this repo to supporters if I ever open a Patreon. Let me know what you think in the comments. So far, we've been writing on the console the commands for compiling, assembling, linking, object copying, and make imaging the files we need every time. The most automated we've done them is to use the shell's history. This is not ideal, nor even optimal. So let's automate the process. The simplest way is to just write a shell script, or a batch file for you Windows users, to build the files in sequence. This is simple enough, just collect the commands we've done and place them one after the other in the file. For Unix, we just add shebang followed by the shell's path. Add -e to tell it to stop if any of the commands fail, set the file as executable, and we're done. And it works. It doesn't even take too long. However, it could take even less long. This is not particularly important at this stage, but as more and more files are added, it becomes important that we don't compile each and every file each and every time. To that end, we have a system called make. If we build the instructions coded in a file called makefile correctly, it will build all files that need rebuilding, and only them. We'll create a very basic makefile now. It will become more complex as our project evolves. There are 2 basic approaches to building a makefile. We'll take the top-down approach. The file we want the whole system to eventually build is called fsl.image, so we'll start our makefile with a rule to build that. Each make rule is split into 3 parts. The first part is the target. This is the file we end up building. The second part, separated by a colon, are the dependencies. fsl.image is built from fsl.bin, so we marked that as a dependency. A dependency means that if fsl.bin changes, fsl.image needs to be rebuilt. Last but not least, we have the recipe. It is vitally important to know that the recipe line must start with a tab character. I've configured my editor to not expand tabs to spaces if this is a makefile, and I suggest you do the same. I'll use some standard variables to make the rules slightly more generic. I'm confident you'll be able to pick up how that works from context. We can take the command used to build fsl.image straight from the build script we wrote before. The next rule we write is not exactly a rule. We will be building a pseudo-target called clean. What this means is that running this target will not actually create a file called clean. This is a standard target almost all makefiles have that erases all the files generated by the build system. In our case, we just erase all files ending with .o, .elf, .bin, and .image. Going to the shell, we run make to build. With no arguments, this builds the first target defined in the file. We can give a target name to build that specific target, so running make clean erases all generated files. Run make again, and this time it fails. The reason it fails is that it wishes to build FSL image from FSL bin, but FSL bin doesn't exist. It did before we ran make clean, and make doesn't know how to build it. So let's teach it how to build it. Again, we copy the rule from the build script we wrote before. Run make again, and this time it's FSL elf it doesn't know how to build. Again, copy the command line from the build script. This time we need dependency on both leds.o and boot0.o. Run in make, we see it is actually trying to build those two files. Make is using built-in pattern rules to do so, or more specifically to try and do so. We won't go into how they're made at this point. Instead, we'll just write our own rules for those two files for now. Copy the rules for compiling and assembling, clean our failed miss attempts from before, run make, and we've got our image. Let's add a rule for flashing the SD card. A dangerous rule, use it carefully. Make sure it works, and we've got a passable make file. This is not exactly the best we can aspire to, but it will do for now. Now let's review the code we ran in the previous video. If you're fluent in contemporary C++, you might wish to skip to the next chapter. We place the base address of the register bank we're writing to, remember that's GPIO bank C, in the confusingly named base ADDR variable. Actually, variable is the wrong name. The const_expr keyword means that this is a compile time known constant and is guaranteed to never change. This means the compiler is allowed to not allocate space for it. We store all register addresses in a variable of type int_ptrt. This is an integer type, but it is the same size as a pointer. This allows us to add numbers to base addresses without the special pointer arithmetic semantics messing with our results. I'll elaborate in a moment. Unfortunately, this also means we need to use a cast in order to actually write the value to memory. C++ has 4 types of casts, creating greater resolution and explicit control for the different functions that the C cast might end up carrying out. Reinterpret cast is a cast that changes the number into a pointer without asking whether that makes sense or not. Bjorn Strostrup, inventor of C++, chose that name because he believes that semantically ugly operations need to be syntactically ugly to match. The combination then turns the address of the register into a pointer, dereferences it, and then assigns it the value we decided it should have. Unsurprisingly, this translates to just storing the value in the address that belongs to the appropriate H616 register. To illustrate my address arithmetic comment from before, let's see what our alternatives are. We've seen that all the registers we're using are 32-bit integers, so we can change the type of our base pointer to a pointer to uint32t. You'll notice that we still need our interpret cast, except now we need it where we define the base pointer rather than where we use it. Except now it won't compile. C++ refuses to treat something that goes through a reinterpret cast as a constant expression. We can change it to regular const, but already we're losing something here. Make the necessary adjustment to the rest of the code, build, install, run, and it doesn't turn on the LEDs. What? The problem has to do with the way C and C++ do pointer arithmetic. When you add 1 to a pointer in C++, the meaning is go to the next element. This means that the actual address increases by the size of the pointed element. Since we're pointing to 32-bit integers here, each offset we gave was multiplied by 4. To make the program work again, we now have to divide by 4 each offset given. Compile, flash, ran, and it works. But was it worth it? To me, the worst thing about this change is that the offsets in our code are now not the same as the offsets documented in the user manual. This means a single glance is not enough to verify we're doing the right thing. So, to me, casting with each use is the more acceptable compromise. We can further improve on it later on. Since we've already added our files to Git, we can simply revert our latest changes. Another thing that deserves explanation is the use of extern C in the code. To get a feeling for why that is necessary, let's try compiling without it. Compilation passes, but linking doesn't. But why? It says it cannot find the symbol reset, but we defined it clear as day. Things become a little clearer when we ask leds.o, where we expect reset to be defined, what symbols it has. We expect to see reset, but instead we see underscore capital Z5 reset V. Huh? I've briefly mentioned this in a previous video, and it's worth repeating. C++ employs name mangling. The symbol defined in the object file is not the same as the one you write in the source code. When you work from C++, that doesn't matter. The language employs the same mangling when you invoke the symbol as when you define it. The problems start to arise when you try to call a function defined in C++ from another language, or vice versa. The exact way the CPU invokes a function is called Application Binary Interface, or ABI. The C++ ABI defines the name mangling completely and consistently. So one way to solve this is to change the name of the function we call in boot0.s. If we replace reset with underscores capital Z5 reset V, everything will work. A simpler solution, however, is to denote the reset function as a function that needs to adhere to the C ABI. We do this by declaring it as extern C. Indeed, when we replace the extern C modifier, compilation passes. Asking for the symbols defined in the object file shows us the function is called reset, with no mangling, pretty much as expected. Which brings us to a question I've referenced a couple of times in the past. How is it okay to write bare metal code, not to mention an entire operating system kernel, in C++? The common wisdom is that the language has too many dependencies and shouldn't be used for anything so low level. There is at least some truth to that common wisdom. The simple truth of the matter is that certain C++ features require extensive runtime support, and thus are incompatible with bare metal and kernel environments. The solution is quite simple. Don't use those features. C++ has quite a lot of advantages to offer over C, not to mention assembly, even without using such features. Of course, that doesn't answer the obvious next question. What if we use such a feature by mistake? In a previous video, I included stdint.h and reassured you all with, trust me, it's fine. How do I know? To answer that, let's try to use something which isn't okay. Let's write a program that throws an exception and see what happens. Compilation passes without a problem. When we try to link, however, we are faced with two types of problems. The second problem is that our program asks to link with a bunch of functions we don't seem to have. The core issue here is that C++ exception handling is done with the help from the C++ runtime libraries. Since we link using the ld command rather than through a C++ compiler, this library is not linked in. That is actually a good thing, as we don't have a runtime library suitable for our runtime environment anyway. In other words, we can try to use any C++ feature we see fit. If the feature we're trying to use needs runtime support, it will simply fail to link. There is no scenario in which we link the program successfully, but then fail to run because we use the C++ feature we can't support. Of course, over time we can simply implement those runtime functions, at which point we absolutely can use those features. Before we get into the first problem the linker complained about, let's recall something I said in the previous video. We were comparing the command line to obj-copy as invoked by uboot versus us. We realized uboot was handpicking which sections get copied, whereas we let obj-copy pick all the sections. Instead, we handpick them inside the linker script. I claim that our way is superior, and I'd like to now show you why. If we look at the errors the linker gave us over the previous example, the one throwing an exception, we can see the message section unknown will not fit in region error. If we look at the linker script file, we can see we created a section called unknown and directed it for assignment to memory region error. This alone makes the error message a little clearer. We also assign memory region error the size 0. The practical upshot of this is that if the unknown section grows beyond 0 size, linking will fail with the error message we've just seen. If we look at the linker script, we can see specific references to specific sections. In other words, the way our linker script is built, anything not explicitly handled by us will go into the unknown section, and if it has any size at all, will cause linking to fail. Indeed, if we look at the sections created for exceptions.o, we can see sections called group and GCC accept table, both non-empty. We didn't tell the linker what to do with them, so the compilation failed. Had we been using the U-boot method of copying just those sections we know we need, the code would have compiled and linked, but the raw machine language would have referenced data that would simply not be there. Which brings us back to the previous question. All C++ features fall into one or more of the following categories. Either they're implemented completely by the compiler or in the machine code, such as stdin.h, they're implemented using custom sections, such as exceptions, or they're implemented using runtime library functions, such as dynamic memory allocation and exceptions again. The first category above is completely safe. The later two can be used only if we write the required support ourselves. These are the unsafe C++ features for us. However, using the linker script with the error memory region, it's still safe to write C++ code as a whole. Either what we write will work, or it will fail at the linking stage. Not only that, if it does fail, we fairly easily get a comprehensive list of the functionality we need to add to the runtime library in order to get it to work. We might fail to compile, but we won't create nonsense machine code. And that's why I dare to write an operating system completely in C++. When we went over the H616 user manual, we saw that it has a block of static RAM at address hex 20000. We also saw that the boot ROM page in the Linux Sun Xi site says that that's the address where execution of our second phase loader begins. And yet, when we looked at the assembly used by U-boot, it starts at 20060. In the previous video, we copied it without going into the reasons, and it worked. But surely, the start address cannot be both 20000 and 20060. That seems like a loose end that needs tying. If we look at the header, we see that the magic number egon.bt0 is the second field in the header. The first field is labeled jump to address. It does not say which address that is, but it pretty much gives us the answer right there. SPL does indeed start execution at address 20000. In order for FEL to load our code, however, we must provide it with this header. So we need our code to start with this mandatory header. What happens is that the header is loaded at 20000 and gets executed. To make that even remotely sane, the header format leaves the first 4 bytes of the header free from outside restrictions. As such, the image creator tool places at the start a jump instruction to the end of the header, which is where it places our code. How big is this header? I think I'll shock nobody when I say it is exactly 60 hexadecimal bytes. So the second phase loader code begins execution at 20000, but our code begins execution at 20060. Mystery solved. As we've seen in the previous video, installing the Egon boot image to sector 16, that's 8 kilobyte offset, works. Different areas on the Linux Sun Xi site, it's not as if we have an official source, claim 2 additional different offsets. The Egon page of the wiki claims that sector 38192 is the correct place. I've not reverse engineered the boot ROM, but we can just try to write our image there. And it doesn't work. Next, the bootable eMMC page claims that if an image is not found at 8 kilobyte, one is searched for at 128 kilobyte. Again, write our image there and nothing again. I have no idea where those claims come from. Maybe they are true to some of the other Sun Xi Allwinner platforms. For the H616, they don't work. Well, that about wraps it up. I think we managed to tie up all the loose ends and hardly created any new ones. If you still have questions, please write them in the comments below. It's always great to hear when people watch and enjoy what I create. Until next time, thank you and goodbye.